So let's get a good, tough example, including dependent sources. And to make this more complicated, I'm going to be sure to define this dependent source not as a function of voltages elsewhere, but as a function of currents elsewhere. And I'll need to define where my I sub x is. Okay, so the question is to find I sub x. So Jesse, what's the first step in something like this?
The first step is to get it into the phasor domain.
Absolutely. Can we move it into phasor domain? What about the circuit tells us we can use phasor methods? Stone?
I just know because I have a cosine there that I'm able to directly turn into like a 20 via the phasor.
That's right. You've got a cosine. There's no U of t. If there was a U of t, you couldn't do phasors. You'd have to use another method. But with no U of t, that cosine's been there forever. All of these components have been there forever. There's no switches. There's nothing changing. So we're definitely in sinusoidal steady state. So let's do this. Let's move right on to our, what's the phasor representation of this source?
Wouldn't that be 4?
True that the omega is equal to 4, but that's not the phasor representation of the source.
20 will be 20, 0, wouldn't it?
That's it. And what's a simpler way of writing 20 at an angle of 0?
Just I was just saying 20 like angle sine of 0 degrees basically. I mean,
you're right that it is definitely 20 at an angle sine of 0 degrees, but what's a simpler way of writing that?
the simple way of writing that would be.
Let's take a look. You've got a real part and you've got an imaginary part. And you're saying that the magnitude of 20 means that you're 20 units out away from the origin. And you're at an angle of 0 with respect to the positive x-axis. So this is your point. And what's the simpler way of writing that?
Wouldn't it just be 0?
Well, this is 0. Right in the middle is 0. You're 20 units away from the origin. But you're right along the real axis line. So you're along the real axis. And you're 20 units away from the origin on the right. So what's that? An easier way to write that?
It would just be cos.
You could say it's equal to 20 times cosine of 0 degrees, but just look at it. You're along the real axis. So it's a real number. It's not going to be 3i or 7i. It's going to be a real number. Maybe it's equal to -7 or +13, but you're 20 units away from the origin. So what's a real number that's positive 20 units away from the origin?
It would be R. I'm honestly not entirely sure at this point.
Yeah, let me write it as a number line. So here's a real number line, and we've got 1. I can't even write 1, 1, 2, 3, and so on. And here's -1, here's -2, here's -3. Here's the origin. Now you know you're 20 units away from the origin. So you're either 20 units to the right or you're 20 units to the left. But you are at an angle of 0 degrees. So 0 degrees is pointing right in this direction. And you're 20 units away. So what would that number be?
I mean, it could just be any number. I mean, it's 0, but it could be anything.
Well, if you start off at 0, and if you move to the right on the number line by 20 units, how far would you be?
20.
20. So the answer is just 20. So that's a much easier way than writing 20 angle 0 or 20 cosine of an angle of 0. Although all that's correct, you can see you're on the real number 20 units to the right. So your simplest representation is just like a 20-volt source. Now the resistor stays the same at 10 ohms. Stone, tell me about this capacitor. What does it become?
The capacitor is 1 over JWC, which
I
think I got.
Impedance of the capacitor is 1 over j omega c, which is.
I think I got -5 over 2.
Let's see. Well, that's 4, and this would be 1/10. So the j comes up on top, and we get the reciprocal of 4 over 10. So that's 10 over 4. So that's -j 5 over 2. Is that what you got? Did you say?
Yep.
All right. Okay.
I'm actually need to ask when I was looking at this, why is J negative in this instance?
Because 1 over j is equal to minus j.
Okay. That makes sense.
How about this? The impedance of the inductor? Jonathan?
That'd be J omega.
J omega L. So what is that?
4J.
That's it. Only because we're electrical engineering, we say J4. Yeah. All right. Can't forget where this current is. We're going to draw it as a capital I sub x now, though, since it's like a DC value. We're in the frequency domain. And this thing has a really easy transform. It's instead of 2 times little I sub x, it's 2 times capital I sub x. And we already know how to figure out the impedance of an inductor. It's J omega L. Omega is 4, as Kyle said. So this is just going to be J2. Quick check. Do all of your resistors have a real impedance? Yes. Do all of your inductors have a positive imaginary impedance? Yes. Do all of your capacitors have a negative imaginary impedance? Yes. So that's done right. Now we can start. Now we've transformed this into circuits 1, and now we can just use circuits 1 approaches. Who's next? Lydia, what is your next step?
I think in the notes you wrote a Z equilibrium, which is like the equivalent impedance.
Oh, not equilibrium, but equivalent.
Equivalent.
If I asked you to find a Norton equivalent or a Thevenin equivalent, it would be. But remember, we're doing nodal analysis, and so we've converted to phasor domain. And what's the next step?
Use a ground.
Choose ground. Yep. Now I know what you're thinking of. You're saying, hey, can't we do anything to simplify the circuit too? And you might be able to. You might be able to do a source transform over here. Are there any impedances that directly simplify without doing source transforms? Are there any impedances that are in series or parallel? Lydia?
No.
No. So the best you could do is source transforms. But if you source transformed, although your 10 would be in parallel then with this guy, you couldn't simplify it because in doing so, you destroy your I sub x. So this is one that you really do need just to use, need to bite the bullet and just use nodal analysis, just the way it is. Your next step is to do ground. And where would you place that ground?
It's at the bottom.
Definitely. We'd place that ground at the bottom. And now we can start doing our work. Let's label our unknown nodes. Is this an unknown node up here? Tim, TJ? Upper left.
It is not. That's 20 volts right there.
Yeah, we know that's 20. How about up here?
We do not know.
We don't know. So we'll call that V1. How about over here?
We do not know.
We don't know. That's V2. How about down here?
0.
It's 0, which we've already called the ground, so we don't need to do it there. Okay, now we can write our equations. Dantre, let's begin. Do you want to write an equation down here?
No,
No, because it's ground. How about up here?
no, because we know it's 20 volts.
Because you know it's 20 volts. So continuing on, let's do it at V1. And remember, we're not saying V1 equals it, we're just doing it at V1. So Dantre, finishing this up, how much current is flowing to the left here?
V1 minus 20 over 10.
Yeah. And help me out. How much current's flowing down?
V1 over 0.
Nope. There's still an impedance.
Oh,
What is
so
that
would it
impedance?
be minus J5 over 2?
That's right. And how about to the right?
V1 minus V2 over J4.
That's right. And all that equals 0. So let's do it for our remaining unknown. John? What is that? John Lightfoot? What's it at V2? How about going to the left?
V2 minus V1 over J4.
That's right. And going down?
We're going down is it negative 2ix.
Yeah, minus 2ix. It's always great when you see current sources in nodal. And then how about going down to the right?
V2 over J2.
V2 over J2. And all that equals 0. So we've got this dependent source. We need an extra equation. Just to verify that we need an extra equation, we have V1 as a variable. We have V2 as a variable. We have IX as a variable. We have three unknowns, only 2 equations. So we definitely need another one. Pavel, what would be an extra one? What's one extra equation that you can pull out of here? Something involving this definition of I sub x.
So you have to do something with Ohm's law.
Yeah, here I definitely would. So you've got this V1, this I sub x. How can you give me some equation involving those things with Ohm's law?
I of x equals V1 multiplied by negative J5/2.
Almost. You just got Ohm's law not quite right. V equals IR, so it would be, you got the right idea. V1 equals IX times minus J5/2. Okay, we got 3 equations, 3 unknowns. We can throw this into a matrix. Let's do this so it's not mysterious. We're going to rewrite this one as asking ourselves, how much V1 is there total? We've got 1/10 over here. Over here, we've got plus J 2/5. See what we did? We just pulled it up. The J becomes positive, minus J in the denominator becomes positive J, and 1/5/2 becomes 2/5. And over here, we've similarly got minus J 1/4. And that's how much V1 we have in our first equation. How much V2 do we have? Let me see who hasn't answered yet. Bobby, how much V2 do we have in this first equation?
Minus 1/J4.
Minus 1/J4. And we could flip that J up to make it positive J 1/4, just a little bit easier to write. And we write all of our constants to the right. So Bobby, just finishing that up, what constant do we have to the right on this first problem?
0.
No, it's hidden in here.
10. Negative 10.
Negative
2. Sorry.
It's -2 on the left. So what is it when we move it to the right?
2.
2, positive 2. There you go. Okay.
Sorry.
Yeah, TJ, let's hear it for V2. How much V1 do we have in this equation?
Well, we've got, I think it's just negative, or it's just J4.
It's J over
J
4.
1/4. Yeah.
Yeah, J over 4. And then, so you want to have, oh, Will, you've been quiet. Let's hear V2.
You're also going to, except for you'll have a negative J over 4 plus a J squared. I can't, is that, or is it just J2?
Oh, that's J2. Yeah, you'll never see J. Yeah, that
Okay.
J2 came from this J2.
Gotcha.
So that's going to be a plus a minus J over 2.
2.
All right. And anything else, Will, as long as I'm there?
I don't see any more constants in there other than the negative 2 IX, but
Yeah, so you got to put that in there too, minus 2 IX, and all that equals, as you said, no constants, equals 0. Okay, and now we can rewrite this, putting all the variables on our left, that would be V1, and then putting this on the left, it would be plus J 5/2 times I sub x, and all that equals 0. Now, with all this, we can throw it into MATLAB. I guess this would be over 20, right? So this would be something over 20. 4 times 5 is 20, so 4 times 2 is 8. And then we're going to subtract from it some other number over 20. I'd have to multiply it by 5. So I think you're all comfortable with saying that this is plus 3/20, plus 3/20 times J. And then on the right, we've got J over 4. And we've got no amount of I sub x. Then the next one, we've got J 0.25. Over here, we've got, let's see, J over 4 plus J over 2 would be a total of minus J 3/4. And we've got minus 2 IX. And then our last one is we've got one V1, we don't have any V2, and we've got J 2.5. So that's V1, V2, I sub X. And all that equals 2, 0, and 0. So now let's plug that into MATLAB.
Sir, did you mean to do 0.1 plus 3/20J, or is it still J? 3/20.
Did I make a mistake? On which line? On the left side or on the right side?
The left side, the first thing you wrote.
The very first thing I wrote. So from up here, the real part is 1/10, so that's right. And then the imaginary part we said was 3/20J, 3/20J.
So the J doesn't have to be in front.
You know, it should be. You're right. It's not wrong if it's not. It's just
So
more
if we put it
standard
in-
math.
If we put in the calculator like that, it wouldn't give us the wrong answer.
Oh yeah, your calculator will give you the same answer if you multiply. Yeah, your calculator says multiplication is commutative, so it won't give you any problem if you put it first or second. So let's plug this into MATLAB. A is going to be equal to 0.1 time plus normally I don't type these things in, but sometimes it just helps to see from scratch how to do it. The next one we said was J times 0.25. The next one we said was 0. Okay, next line was J times 0.25 minus J times 3/4 minus 2. The last line was 0, it was 1, 0, and J times 2.5. Our B is 2, 0, 0. If you don't remember how to solve things using MATLAB, take a look at your EE120 book. We've got a section where we not only solve simultaneous equations using MATLAB, but we solve simultaneous equations that are imaginary, complex using MATLAB. So these are our V1, our V2, our IX. And the question just asked for our IX. So our IX is the third part of our answer, which is this. And it also, although this is correct, we want to convert that into polar notation. So I'm using a program that I wrote, rectangular to polar, that I wrote back in EE120 to convert that. Oh, but if you didn't have that, you could have just as well said, here's your IX. What's the magnitude of it? It's the absolute value of IX, which is 7.59, same as my thing returned. And what is its angle in degrees? Well, that's its angle in radians rather. And then to convert it to degrees, you just have to multiply it by 180 divided by pi. And that's our 108. So it's the same thing as we got over here. And we can write that down. So our I sub X is equal to minus 2.4 plus J 7.2, which is equal to 7.59 at an angle of 108. And somebody tell me, what is the last step to find the answer to our question?
Convert back into the time domain.
Absolutely, don't forget that. So 7.59 cosine of 4t plus 108, and that would be all in amps. And that's the answer to our question. And this is also a good example about why it's useful to have that TI 89 or higher and why it's important to get used to it. I can't help you on the exam using your calculator. So you definitely want to get some practice putting in these matrices now. That was a pretty complicated example question. Do you have any questions for me?